Hello. So today I'm going to start chapter 7. So far, I tried to I tried to match the end of the lecture to the end of a chapter. Usually, I do not want to mix two chapters in one lecture, but chapter 7 is so closely related to chapter 6, so it's more natural just to continue to chapter 7. So let me start. Chapter 7 is about sampling distribution, which is another level. We are going to another level, so pay more attention. It will be more difficult, and maybe I guess you so far maybe most of if you most of you may have heard about probability, average, like normal distribution, bell curve. Those kind of things are commonly used in your daily life, but sampling distribution is a kind of very unique and very confusing concept in statistics. I think it's really important concept in statistics, but frankly speaking, many people, even many statisticians, many statistics teachers, do not understand what is a sampling distribution, and they are not good at teaching this. So let me try. I'll try. Give it a try. So why do we care about sampling distribution? The ultimate goal of so far, the chapters 1 through 6 only consider theoretical properties of some object, like what is the property of probability, what is the properties of mean and variance, what is the properties of binary, binomial, or normal distributions. So we only learned how they behave if under certain circumstances or assumptions. But so far there were no data. So I just vaguely explained there is kind of a data set corresponds to that concepts, but it does not require all the topics do not require any data, and it's so. However, what we are going to do in practice is a more serious inference, statistical inference, which is not what we learned yet. So we are going to learn statistical inference methods from now on. For example, we want to estimate some parameters of interest. So in the earlier chapters, we assumed that parameters are given and studied properties. But actually, you have to estimate the parameters. Parameters are unknown, only you observe the result. But in the previous chapters, we assumed parameters are given, and then we studied what happened in the observations, right? Given parameters, what's going on in the observations. But in practice, we observe the data and we have to guess what's going on in the parameters. So we have to go the other way, and to go the other way, we have to learn what happens theoretically if we knew the parameters. So this is what we learned in the earlier chapters. To go the other way, we had to learn how the data were generated from the parameters, or how the data behave given parameters. So that's what we learned. But from now on, it will be different. We will consider data directly in relevant chapters. So let me start with this simple question, warm-up question. Say X is a random variable for a randomly chosen person's annual income. So you randomly choose a person on the street and ask her or his annual income last year. And it is random. And then you write equation this way. X, random variable X, follows normal distribution with parameter mu and sigma squared. Then what is random when you write this way? In this notation, you have x, mu, sigma squared, and what's random among them? There is no trap, so there is no trick. So just guess and just choose whatever come to your mind. The answer is x. So think about it. Only x is random because random. When I say random, randomness is generated by an experiment, and in that example, in the question, the experiment is to choose a random person. And when we say something is random, that means if you repeat the experiment, the outcome may be different, right? So then we say that is random. So different experiments can have different outcomes, so the outcomes are random. Otherwise, if they are the same, then it is not random, right? So then it is more clear. X, if you choose a different person, x will be different. The answer will be different. That is random. However, the mu and sigma squared, mu is the mean, sigma squared is the variance. Mu and sigma squared are determined by everyone, the whole distribution. So mu is the average income, which is not determined by one single experiment or several people. You need to know everyone's income. So in some sense, everyone has the same mean income. Average income, say for example, what is the average income in the United States? I don't know what exactly that is, but what's clear here is any person lives in the United States has the same average income. So, right? Because they belong to the same group, and the group has only one average income. So that means no matter who you choose, the mean is the same. The variance is the same because it's determined by everyone. That's the concept of population. So there is population, the whole group, and the parameters are determined by the whole group, not by a few observations or experiments. So right, it's clear then. Now it's more clear what is random and what is not. Okay, then if you understand what is random, then also it is obvious to say if something is random, you can define the probability distribution, right? And if it is random, then you can calculate the mean and the variance, right? So we learned how to calculate them. So of course, to calculate the mean and the variance, the object should be a number, but let's assume that's kind of minor problem. So if you agree, let me make it more confusing. Right? Instead of asking one person on the street, now there is a research center. So a research center conducted a survey of 1,000 people. So the center chooses 1,000 random people, and ask each of them about their annual income last year. So you collect 1,000 observations of income, and then you calculate their average income, average annual income from 1,000 people. And we are going to denote that average as X bar. X upper bar, will be the average annual income from that survey. Then, do you think X bar is random or not? It's a little bit more tricky, but it's important to think about this. So, the answer is yes, it is random. Yes, it is random because it's parallel. So earlier I said something is random if different experiments can give different outcomes for that, right? So in this case, an experiment is a survey. So if you, let's put this, X bar is random because the average income is calculated from 1,000 people. And if you survey different set of 1,000 people, so if you randomly choose 1,000 people again, then you will encounter different people. So they will give you different average income. The results may be similar, but usually different, right? So the X bar, the average income from a survey depends only on 1,000 people, which is just a small part of the population, right? So depending on how you choose 1,000 people, it will be different. The realization will be different. That's why we say we have to understand X bar as a random variable. The average is random, right? Exactly the same rationale. There is no difference. 1,000 people is just a part of the larger population. But major and also then what corresponds to the experiment is a survey. So if you repeat an experiment, you will get a different result. That is randomness. Then in this example, in this survey example, one experiment is one survey. So if you redo the survey, you are going to get different average. That means one experiment consists of 1,000 people. That's the major difference. The difference between choosing one person or doing a survey is just how many observations you get at the same time in one experiment. In a single individual survey, single person is one experiment, but now the survey consists of 1,000 experiments, right? And that 1,000 experiments will be again considered as another one larger experiment. So repetition of the larger experiment means choosing another 1,000 people, randomly choosing 1,000 people again and again, right? So that is random sample. This is the basic concept of random sample. So random sample is a collection of observations. You in one experiment, in one survey, in one experiment, one larger experiment, you observe more than a single outcome. So usually denoted by x1, x2, xn. So subscript, it's indexed by subscript. So if you survey 1,000 people, n will be 1,000. And so n denotes the size of random sample. So how many observations you get in one large experiment, right? That we call a random sampling. Additionally, we are making two assumptions on a random sample on the observations. So for a set of observations to be a random sample, it has to satisfy these two assumptions. One is identical distribution. So the observation, so like if you conduct a survey of 1,000 people, the 1,000 people should be from the same population. For example, if you are interested in the distribution of income in the United States, then you have to choose from among the people living in the United States. For example, if someone is not in the United States, then if someone is from Europe, from China, like from elsewhere, then they may have different distributions. So the identical distribution assumption is broken. All the observations should be from the same population group, same distribution. And the second assumption is independence. As you know, like all the observations have to be independent of each other. So the first person's answer has no correlation or does not affect the following respondents' answers. Therefore, so x1, x2, x3, all the guys have nothing to do with each other. They don't know each other. You are randomly choosing a person. So these two are critical assumptions for a random sample. So as I said in the previous chapters, we considered one experiment equals one observation, which is not wrong. That's the basis, more fundamental structure of randomness. But from now on, we are going to consider the experiment as a random sampling. So, like making a random sample is random sampling. So, surveying 1,000 people will be considered as one experiment, and we call that large experiment as random sampling. So, you observe n number of observations from one experiment, which is one random sampling. And from the random sample, you may calculate the mean, or you may calculate a different thing. And no matter what you calculate, the result will be random, because if you do another random sampling, then your calculation results will be different. The average or the variance, whatever probability calculated from the data, depend on who you sample, right? So, and then because it is random, earlier I said an obvious statement. If something is random, you can define its probability distribution, and if something is random, you can calculate its mean and variance. We are going to do that in the next lecture. X bar. Today we learned the average calculated from a sample is random. So then our natural question is, okay, then what is its probability distribution? What is its mean and what is its variance, right? So we will study that, which is really important in statistical inference. So I will continue that in the next lecture. Okay, thank you for watching, and see you later. Bye bye.